Oops, I got the N and the R mixed up. This is the correct relationship. This is our decay rate, which is dN dt. So that's in particles per second. That has the right units for decay rate. And that's equal to minus lambda times n, where lambda is our decay constant. So this is the correct relationship. Okay, so if we then have a larger number of particles, we're going to have a bigger decay rate, because any given particle will decay at a certain rate. And so the decay constant then is basically the probability that a given particle will decay. In a certain time. So this is related to the tunneling probability that we talked about before. But for the problem that we're looking at here, we can figure out lambda from knowing that the half-life for plutonium is 25,000 years. Okay, so that's what I'm going to want to do. Now, how did I get this relationship? Well, this shows us that there's an exponential decay. It starts out at time equals 0, n is equal to n naught. So here at time equals 0, we have n equals n naught. But then after one half-life time period, n equals 1/2 n naught at t equals t half-life. Because we just looked at the definition for a half-life. That's the amount of time that it takes for the particle sample to be cut in half. Okay, so when we get down to this point, we're at 1/2 n naught. Then this value here is going to be t 1/2. And that's going to continue to drop off as an exponential decay function. Now, why is it an exponential decay function? Well, that comes straight back from this relationship here. If we just do a first order separable differential equation, pretty simple one for us to do with our math experience, we can just rewrite this as dn over n, separable, equals minus lambda dt. Integrate this from n naught to n as a function of time. So we integrate this from 0 to t. And on the left-hand side, we get the natural log of n over n naught equals minus lambda t on the right. Then if we exponentiate that, both sides of the equation, we get n over n naught equals e to the minus lambda t, or n equals n naught e to the minus lambda t. So, to specify the particular curve that we're looking at, we need to know what the decay constant is, the lambda value. And we can get that, we can get lambda from this information here. So let's do that. So if we write in for the half-life time period, 1/2 n naught equals n naught e to the minus lambda times t 1/2. Then we can cancel out the n naughts, and we get that the natural log of 1/2 is equal to minus lambda t 1/2 power. Okay. So here I just took the natural log of both sides of the equation. The natural log of e to the minus lambda times t 1/2 is just the exponent of the exponential. And then log of 1/2 is minus the log of 2. So we have minus the log of 2 equals minus lambda times t 1/2. Or lambda equals natural log of 2 divided by t 1/2. Okay, so natural log of 2 is 0.69. And then divide that by t 1/2, that's 25,000. That gives us a decay constant that's equal to two 0.76 times 10 to the minus 5. And so what's the physical significance of this? This has units of 1 over year, because I measured the half-life time period in years. And so what this tells us then is that there is 2.76 100,000ths of a chance that a given plutonium atom will decay in 1 year. So this is our decay probability. Any given plutonium atom has a 1 chance in 276,000 of decaying in 1 year time period. So you might say, well, that's not very much. Why are we so worried about plutonium? Well, because the number of particles can be so big. That's why we're worried about it. And so if we want the decay rate, dN dt, that's equal to minus lambda n. So let's set n here equal to the number of particles. Let's make it 10 to the 24th power plutonium atoms. So if that's the case, then dN dt at this moment, when the n value is 10 to the 24, will be equal to minus lambda times n. So that would be the minus is just coming from the fact that you're losing particles, so it's going to be a negative change in the number of particles. So that would be 2.76 times 10 to the minus 5 multiplied by 10 to the 24, or that'll be minus 2.76 times 10 to the 19th power decays per year. Now if we want decays per second, which is a more typical kind of a question, then you could convert years to seconds. 1 year is equal to about pi times 10 to the 7 seconds. So we see this is going to be something like a trillion decays per second. And so that's a lot. You know, even though there's only 1 chance in 276,000 of a given plutonium particle decaying in 1 year. If you have a trillion decaying per second, that is a pretty big deal. So that gives us 8.9 times 10 to the 11 decays per second. That's been determined. I don't know if this is accurate or not, but I heard an estimate that if you could take enough plutonium, say a tablespoon of it, and administer it properly, you could kill everybody on the planet with just one tablespoon of it. And so this is extremely toxic stuff. We might also ask here, well, if it's this toxic, then how long do we have to wait for it to decay to a safe value? Let's say 1/1000th of its original value. So it's going to be way down here somewhere on this decay curve. So we're at 1/1000th of n naught. What's this time going to be when the value for n is 1/1000th of the original value? So we could put in here 1/1000 times n naught, that's n, equals n naught e to the minus lambda times t. And then t is what we're going to want to solve for here. So we have 1/1000th of n naught equals n naught e to the minus lambda t. So you have the log of 1/1000 equals minus lambda, which is 2.76 times 10 to the minus 5 times t. And so this is the natural log of 1,000. And there's a negative out in front of that. So that's going to cancel out this negative. So you have natural log of 1,000 divided by 2.76 times 10 to the minus 5. That gives us 248,000 years. Which is almost 10 half-life time periods. Should that make sense? Well, sure. Because if you cut it in half, that's 25,000 years. Cut it in half again, that's 50,000 years. Cut it in half again, that's 75,000 years. Cut it in half again, that's 100,000 years. And so, roughly speaking, this is 10 half-life time periods. Okay? And 2 to the 10th power is about 1,000. Okay? And so it's about right that you would have to wait almost 250,000 years for your sample of plutonium to decay to what we might arbitrarily consider to be safe values. Now, is this safe at 1/1000th of its original? Well, not necessarily. If 1 tablespoon could kill everybody, then that still may not be safe.